Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be starting Chapter 11, which is our first chapter that we're going to look at in second semester, dealing with chemical reactions. Now, when you think of chemistry, you're really thinking of this chapter because what we're going to be looking at is an in-depth look at how and why chemicals behave in the way in which they do and how they react with each other. Now, chemical reactions, if you recall from first semester, we talked about chemical versus physical changes is a process where atoms of one or more substances are rearranged to form different substances. You actually have a change in identity in a chemical reaction. Now, one of the things we looked at in first semester, way back in like chapter 3, was, how do we know when we're just looking at on a macroscopic level when we've got a change happening on the particle level? So we looked at evidence of chemical reaction. So we talked about how identity causes color. So when you have a change in color or a solid gets formed that wasn't there before, that's usually a dead giveaway. You have a new chemical identity or a change in chemical identity. And we looked at in the ionic compounds chapter, we did the ion lab. We mixed clear colorless solutions together and bam, all of a sudden out of nowhere, different color solids appeared in the liquid. We called those precipitates. That was a dead giveaway. We had a chemical reaction. If you have an odor produced that wasn't there before, or gases that weren't there before, that's a good guess that you've got a chemical reaction. And then often the evolution of large quantities of light or heat can be indications that you have a change in chemical identity. But this one's a little bit trickier. In fact, all of these you can come up with a way. Well, when you paint a wall, you're not really chemically changing the wall, but the color's changed. Well, remember, you didn't change the color of the wall. You just put something on the outside of it. But all chemical and physical reactions involve light and energy. So it has to be a more overt or see other clues to often know. But what's happening on the particle level? So when we see something at the macroscopic level, we may have a clue whether something has changed at the particle level. But really, when we're looking at balancing chemical reactions and studying chemical reactions, we're getting down to the particle level and describing exactly what we see. So one type of description would be a word equation. Now, this is a step in the right direction to make it look more like a chemical reaction because we can just describe in words. So we could describe what we see. This reacts with this to make that. Well, we can take that and make it look more like an equation when we write a word equation. So it's a chemical reaction translated into an equation using the names of the substances for our reactants and products. And we separate the reactant and product side by the yield sign, just like you talked about probably last year in biology. So for a chemical sentence like using electrolysis, water is broken down into hydrogen and oxygen gases. Well, water is what we're starting with, so that's going to be a reactant. And then that's breaking to produce two new substances, hydrogen and oxygen. So that would be what a word equation is. So it's a step in the right direction for making a balanced chemical equation. But it really still has some key ingredients missing if we want to get to the particle level, and that's the formulas. Word equations are use chemical formulas. Um, I should say, if we take a word equation and write the words as formulas, we go from a word equation to a formula or skeleton equation. It's still just the bare bones because it's missing some really key things we're going to talk about later, but it does include at least what the particles are we're dealing with, so you can see the formulas inside it. So water yields hydrogen, oxygen. That is more descriptive if we write that as a formula or skeleton equation. Water is H2O, and if you recall from first semester, when we're talking about elemental substances, and we'll review this in a second, if it's one of the diatomics, we have to write it with a subscript 2. So hydrogen is a diatomic, that's H2. Oxygen is a diatomic, that's O2. So this is what's known as a formula or skeleton equation. Closer and more descriptive, but not quite all the way to where we want to be to get an accurate look at what's happening on the particle level. Now, just a quick review, because if you have words and you want formulas, that means we've got to remember some chemistry here. And we're definitely going to do this later on in the chapter. So remember, elements, you have to ask yourself if it's a diatomic molecule. And remember, Han Fickelbrei is one way to think about that. Han, H-O-N, Fickelbrei, write down the halogen row, fluorine, chlorine, bromine, and iodine. Those 7 elements are always written as a diatomic. But if they're not one of those 7, we just write it as a single element. So it's monatomic. So something like silver, it's not a Han Fickelbrei. It's not one of our diatomics. So we just write Ag, its symbol. But if we had something that was diatomic, we need to remember to put a subscript 2. So chlorine, Cl2, hydrogen, H2, oxygen, O2, nitrogen, N2, and so on. And that's a really important thing because if we're counting atoms, we need to have an accurate formula in order to do that. Now that's elemental substances. What happens if we have a compound? Well, if you recall, in first semester, we answered how you know what type of compound it is. It could be a molecular substance. Remember, all nonmetals, typically molecule. It could be ionic, which means it's going to start with a metal or ammonium. And that's why I didn't say all nonmetals are always molecular, because ammonium is a nonmetal cation. So it could be all nonmetals, but still have ions. That's ionic. And then finally, it could be an acid. And remember, acids are things that start with H. We might see acids, but they're going to be very rare. Most of the time, we're actually going to be talking about ionic compounds. And sometimes we're going to see molecular compounds, but those are a lot rarer and usually a lot easier. So the important one here is ionic. Now, as a review, remember molecule. Pretty straightforward. You just translate the prefix. Carbon dioxide, CO2. And most of the molecules we deal with are that basic. Things you know, like carbon dioxide, so they're pretty easy. So when we run into a molecular thing, it's usually more straightforward. Now, if we run into an ionic thing, which is what it is most of the time, that means find the charges by looking on the back of the periodic table, and then find the smallest ratio of cations to anions that would give us a neutral compound, which means crisscross reduce. So barium nitrate, barium, if you look it up, is a Ba2 plus, nitrate is NO3 minus. If I had one of each, it would have an overall charge of positive 1. That's not neutral, so it can't be BaNO3. So how do we figure it out? Well, a quick way is crisscross reduce. We need 2 nitrates for every 1 barium, so we would write that as BaNO3 in parentheses 2. Remember this because most of the compounds that you're going to end up making are going to be ionic compounds. So you'll do this more than anything else. Now, technically, it could be an acid, and I'm not sure if you're going to run into any, but just a reminder, the anion determines the name for an acid, because an acid, our molecular acids that we're going to look at in name, are going to be um, hydrogen stuck to some anion, making a molecular acid. And if it came from a anion that ended in "ide," it became hydroic. If it came from an anion that ended in "ate," it was ic acid. And if it came from an anion like nitrite that ends in "ite," it becomes nitrous acid. We looked at it first semester. Hopefully you remember it. Probably not going to happen that often, but that's how you would handle it. If you really see an acid, more often you're going to be doing this way. You're getting its formula most of the time. So you need to remember, oh, chloric, well, that comes from chlorate. So you look up chlorate, that's ClO3 minus. Well, it's got to be neutral, so I only put one hydrogen because hydrogen's a plus one. If it was carbonic acid, that comes from carbonate, CO3 2 minus. It has 2 hydrogens stuck to the beginning of it. So if you have an acid, usually it's going to be more basic like this. But most of the time you're going to be talking about ionic compounds, and that's the one you got to be most familiar with. Now, there are things called common names that we run into. The biggest one is going to be water, and that's one that's kind of a no-brainer at this point. Most people know water is H2O. So the word equation may have said water. You got to remember it's H2O. Now, another one that's not as common but could happen is ammonia. Ammonia technically is molecular. It's nitrogen trihydride, but we never write it that way, just like we don't say dihydrogen monoxide for water. So ammonia is another common name. I tried to think of a couple of, any other instances where it might have other things. So a couple of others I came up with. You're probably not going to see them, but this is what I mean by this idea. Sometimes people will say table salt, but table salt is sodium chloride. That's NaCl. And sometimes I refer to NaCl as salt and expect somebody to know that that's what it is. Same would be true for something like table sugar. Now, you don't need to really worry about this one because you're never going to see it, but I just wanted to extend the concept. Sugar is actually sucrose, and that would be C12H22O11. But we don't usually call it sucrose, and it doesn't really come from the name sugar that it's going to be C12H22O11, but that is really what it is. So those would be examples of some common name. A really important one is water. And you might need to be familiar with ammonia. Just remember ammonium is NH4 plus. Ammonia is close to that. One way to remember it. Now, something that is going to come up a lot, and you really should be comfortable with all of these for the test, is what the different symbols in an equation mean. Well, plus does not mean add. What plus is used to do is to separate different reactants from each other and different products from each other so that we separate them and understand we're talking about different substances. So think of it as an and. You have this and this and this making this. So think of a plus as a separator, and it literally translates almost as and. Now, the arrow you're probably familiar with from biology, that is the yield sign, and all it really does is separates reactants from products. It establishes what you're starting with and what you're ending up with. Now, sometimes you might see a double arrow. Now, we want to keep the convention that reactants are on the left and products are on the right. But that double arrow would then mean not only do reactants form products, but products go backwards and break apart into reactants. That's known as a reversible reaction. Won't see that too often in this chapter, but in second semester we will see it a lot when we get into equilibrium. S, L, and G. So if you see a formula and in parentheses you have an S, an L, or a G, that stands for what state? Solid, liquid, or gas. So it's just telling us the state. Now, aqueous is kind of like a state. It's not really one of our states of matter, but in terms of how it exists in what form in a chemical reaction, it kind of is like a different state. When you have a substance that's dissolved in water, it becomes aqueous. So it's not really a solid or a gas. And often we're talking about solids here. So it would be a solid if it weren't dissolved in water. But since it's dissolved in water, it's broken apart into its ions. So the aqueous means it's dissolved in water. Now the next one, I think the second symbol kind of gives it away. If we have to add heat, in other words, the reaction is absorbing energy, you may see that written. Because if it needs to absorb energy to occur, energy is something that's necessary for reaction. Sometimes we will denote that with a triangle or with a heat. And then finally, if we have a substance written above the arrow, you are talking about a substance that's not a reactant or a product, but still an important part of the reaction, and that would describe a catalyst. So a catalyst is something that's there at the beginning and there at the end. So it affects the reaction rate, makes it happen much faster. Without it, the reaction is going to be a lot slower. But it's not really a reactant or a product per se, because it's there at the start and it's there at the end. So it speeds up a reaction without being used. Technically, and we'll see this in a future chapter, it is a part of the reaction. It just is reacted away at the beginning and then later gets produced. So we start with and we end with it. It seems like it does nothing. But since it's not really a reactant or a product in our balanced equation, we put it above the arrow to avoid confusion. Now at this point, I want you to watch the movie Chemical Equations that was right below this as kind of a nice overview of this idea. But we're going to move forward and look at balancing equations. Now, fundamentally, we're going to look at 6 different rules for balancing equations. And I'm going to individually look at each of these. And actually, all of my examples come right off your homework. So as we're going through this, you might want to have out your balancing equations homework assignment. So we're going to look at these ideas with real problems from your homework. So number 1, make sure you have the right formulas. If you're going to balance chemical equations, and what that means is we're getting the right number of atoms on each side of each type. So you can't create or destroy atoms in ordinary chemical reactions. All we can do is rearrange them. So if we start with 32 hydrogens and 16 oxygens, that's what we have to end up with. So when we're balancing equations, we're balancing the number and the type of atoms on each side. Now, first, without a right formula, there's no way I can count atoms properly. So water, it's got to be H2O. Hydrogen and oxygen are both diatomic. They have to be written as H2 and O2. Otherwise, I might be able to balance it, but it's not going to be valid. Which brings up something I want you to understand before we really get into true balancing here. When we're balancing equations, we're putting in these numbers and getting things equal on both sides. And students start to develop the feel that what they're really doing is making up numbers to make things equal. Well, you're not really making up numbers. What you're actually doing is discovering the quantities that actually exist in the real world. And we're doing that through the process of balancing. So you're not making anything up. What you're doing is you're finding out how it really reacts. So if you get a balanced chemical equation that's valid, that actually shows you exactly how this thing reacts. It's a recipe for the reaction. So what we're really doing here when we go to balance, we're not making stuff up. But if you don't start with the right formulas, there's no way you get the right balanced equation. So when I look at that, I started with 2 oxygens. I ended with only 1. That can't happen. But if I put a 2 in front of the waters and I made 2 waters, I still have the right formula, H2O, but now I'm going to end up with 2 oxygens. Now that also means I got 4 hydrogens because H2 doubled is 4. So that would mean I need to start with 2 hydrogens. And it would also mean I only had 1 O2. So technically I would put a 1 there. This is the process we're going to do when we balance equations. And that's exactly what we do. We bounce back and forth, putting numbers in front until the numbers of each type of atom are equal on both sides. And you need to understand that if I started with the wrong formulas, there's no way I'm getting a 2 to 1 to 2 balanced equation. So if I wrote down oxygen as O, it's going to look like a 1 to 1 to 1 balanced equation. But I guarantee in the real world, if you make water through this reaction, you're going to need twice as much hydrogen as oxygen, and you're going to make the same amount of water that you used up hydrogen. and you will make twice as much water than you had oxygen. That ratio is etched in stone, and that's exactly how this reaction occurs. So remember, we're not making something up. We're discovering how it really exists in the real world. And 1 to 1 to 1 is not how this reaction will occur in the real world. So that bottom reaction, completely invalid, simply because it doesn't have the right formulas and therefore it doesn't express how the reaction really occurs in the real world. Second, I know it might be easier to sometimes mess with formulas, but we can only balance things by putting in the blanks here. That spot in front is where we put what's called the coefficient. So what we're really doing is adding numbers in the coefficient spot to balance things. And we can't put numbers anywhere else. I know it might work if we erase that 2, but oxygen is O2. It's not O. I know it might work if for some bizarre reason a student stuck a 2 in the middle there and said that means you got 2 oxygens and you started with 2 and you ended up with 2, but that makes absolutely no sense. And then finally, we can't just stick a 2 there. I mean, that makes more sense. H2O2 is a real substance, but it's not water. So we're not going to get the right balanced chemical equation. So you only can add numbers in the coefficient spot. You can't change or add numbers anywhere else. Next one, most important rule of balancing. Keep it simple. Start with atoms that appear only once on each side. They're easier to balance. It's easier to balance 2 objects than it is to balance 3 or 4. So keep it simple, most important rule. And what that typically means, like you can see in this reaction, that means you're usually going to do hydrogen and oxygen last. I have oxygens in every single compound. Right now, I would have to make up 4 numbers off the top of my head to try and make them equal, and that's incredibly hard. Hydrogens are in 3 of the 4 substances, so that's going to be harder. But if you look at sodium, it's in one spot on each side. If you look at sulfur, it's in one spot on each side. Those are very easy things to balance. So in this case, I would do the Na and the S first. And how I would do that, something like sodium. Now I know on the left I have NaOH, that's 1 sodium. On the right, Na2SO4, that's 2 sodiums. Starting with 1, ending up with 2, that can happen. That means I needed to start with 2. Well, if I put a 2 in front of NaOH, I now have 2 NAs. So I'm not changing anything, I just am saying I need twice as much NaOH as I thought I needed. Now that would imply I really had a 1 there, so remember that. What I really did is I figured out that was a 2 and that was a 1. And you don't have to write the 1 because it's understood if it's empty that it means 1. But when you first start out, it is useful to put that 1 in there because it basically says, I'm not unsure about what this is. I think it's a 1. So leaving it blank, is it a 1 or you don't know? Put a 1 then, makes it easier. So that balances the NAs, and now if I look, well, there's 1 S on each side, so they seem fine. Now I'm going to go to the next thing. Now, in order for there to be 1 S on each side, that means I technically had a 1 over there as well. So I'm guessing that's a 1. And keep in mind, when we do this, we may be wrong. So we may have to erase things. So always use pencil. So now I'm ready to try hydrogen because I just made a guess. I've guessed that I definitely have, well, I think I have 2 oxygens or hydrogens on the left. And in water on the right, H2O, I have 2 hydrogens. So it looks like I just need, if I'm doing X next, oh, I'm sorry. I need to back up. Remember, sometimes we make mistakes. Well, I made a verbal mistake there. You always have to look. Remember, we had hydrogens in 3 places. So when I stuck that 1 here, that meant I have 2 hydrogens here. But notice I also have hydrogens here. 2 NaOHs means I have 2 hydrogens there. 2 plus 2 is a total of 4 on the left. So I can't just have 1 water. If I need 4 hydrogens, that means I need 2 waters. So always use a pencil. Now finally, I'm ready to do oxygen. Well, I've already made a guess everywhere. So by saving oxygen to last, I already think I've got it. So double check it. I have 4 O's here. In 2 NaOHs, I have 2 O's there. That's a total of 6 on the left. I have 4 O's here. In 2 waters, I have 2 O's there. I've got 6 on the right. Yep, waters are good. So I didn't even need to do the hardest thing in the whole, or the oxygens are good. I didn't even need to do the hardest thing in the whole thing to balance, which is the oxygens. All of my other guesses took care of it for me. This is the single most important thing to do. Keep it simple. Now, a related concept to keep it simple is if we see polyatomic ions on both sides, and you should recognize these because we did a whole test with, and a whole chapter, multiple chapters where we talked about polyatomic ions. Polyatomic ions are a group of atoms that are together, and if you see them on the left and on the right, that means They stuck together in the reaction. And we can keep it simple by treating that whole thing, that whole entire polyatomic ion, as one unit and balancing it that way. So when I look at this problem from the homework set, I see I've got a nitrate, NO3, on the left and on the right. So the anion NO3 is actually on both sides. Well, I can balance the N's and the O's in one shot by just balancing NO3s. Now, I have a 2 outside of the parentheses on the right, so that means I have 2 NO3s on the right. Well, if I ended up with 2 NO3s, that means I had to start with 2, which means I need a 2 in front of the silver nitrate. So I've got to put a 2 there. And remember, that also means I'm guessing that's a 1. Now, to finish, I would continue on and then balance the AGs and then balance the MGs. But chunking the NO3s makes it easier to do this problem. So instead of 2 separate elements, I did both in one shot. Now, in this particular problem from the homework, you've got polyatomics everywhere. So maybe the last one you could have done without chunking the polyatomics, but here it's going to be significantly easier if you learn this technique. So we've got NH4s and CO3s and PO4s, ammoniums and carbonates and phosphates all over the place. So we're filled with polyatomic ions. So we can balance a lot of individual P's and C's and O's and so forth, or we can balance them in one shot just by chunking our polyatomics. And remember, when I balance the H's in NH4, I'm not balancing all of my H's, I'm balancing those H's. So you do need to look beyond your polyatomics. But when I balance my NH4s, I don't need to worry about those N's and H's anymore. And we're going to start with ammonium because it's a really important one to get here. And you're going to see this from time to time. You have 2 NH4s on the left and you have 3 NH4s on the right. 2 can't equal 3. So what you need to understand is, okay, what's the smallest number both 2 and 3 equal? Well, they both can equal 6. So what would I need to do for coefficients to make 6 on the left and 6 on the right? Well, if I put a 3 in front of the ammonium on the left, 3 times 2, so I had 2 and I'm tripling it, that's 6. Now I've got 6 ammoniums on the left, and if I put a 2 in front of ammonium phosphate, now I have 6 ammoniums on the right as well. So putting in a 3 and a 2 has now balanced my NH4s, and all of those N's and H's in those ammoniums are taken care of. So we don't need to worry about those N's and those H's. They're done and already fixed. Now to finish off, notice I got some other hints when I put in those coefficients. When I put the 3 in front of ammonium carbonate on the left, that means I have 3 carbonates. I've only got 1 carbonate on the right. So I should stick a 3 right here, and that would balance my carbonates. And I also have a guess about phosphates. Once I push that 2 in front of the ammonium phosphate on the right, that gave me a good guess for exactly how many phosphates I need on the left side. And then that would then help me balance my hydrogens that are left. So work through this one on your own, but that's what I mean by chunk, and it makes it significantly easier. You can save massive quantities of time and make hard problems much easier if you do that. Next one are just some tricks if you're having trouble. And there's 2 specific situations that might be useful to you. The first one is when we have what's called hydrocarbon combustion. Hydrocarbons are compounds, molecular compounds containing hydrogen and carbon, hence the name hydrocarbon. Hydrocarbons are all flammable, which means we can burn them. And if you know anything about combustion or burning, you know that means you need air. But most chemistry teachers will say, well, wait a second, it's not really air you need, it's oxygen in the air. So whenever you see a hydrocarbon oxygen, you're going to get CO2 and H2 on the right side. So that's actually something we're going to learn later and use. But for now, when I see this kind of hydrocarbon combustion, you need to realize about half the time I'm going to run into trouble. And this idea of when in trouble double, that rhyme, is going to become useful. But it most often happens when we've got hydrocarbon combustion. So let's work the process. And remember, use pencil because we might be wrong. I've already seen that once on here. Here we're definitely going to be wrong. So C2H6 plus O2 makes CO2 and H2O. Got oxygens in 3 spots, hydrogens in 2, and carbons in 2. I'm going to start with carbons, so keep it simple. I've got 2 carbons on the left, so I need 2 carbons on the right. That means I need 2 CO2s. Now next I'm going to go to hydrogen, because remember, I'm saving O's for last because they appear in more compounds. I have 6 hydrogens on the left, because it's C2H6. And I was thinking I had 1 C2H6 and put the 1 there, but that's what I'm implying. So how many waters would I need? Well, I would need 3. That would give me 6 hydrogens on each side. Now finally, oxygens. Well, if you look at the oxygens, remember they're in multiple spots. This is what I showed you a minute ago when I made a mistake. You have to account for both oxygen sources. So 2 CO2s, that would be 4 O's. 3 waters, that's 3 O's. 4 plus 3 is 7. So I need 7 oxygens on the left. There is no way I can ever make O2 equal 7 with a whole number. I'm in trouble. So what does the rhyme say? When in trouble, double. So what I'm going to do is I thought C2H6 was 1. I'm going to put it as a 2. So I'm going to double it. Now that gives me 4 carbons, which gives me 4 CO2s. And that gives me 12 hydrogens, which means I need 6 waters. That's 12 hydrogens. And now when I count my oxygens, 4 times 2 is 8, plus 6, that's 14. O2 double, or what in front of O2 would give me 14? Well, 7 times 2 gives me 14. And notice I'm double what most of my predictions were before. I thought this was a 1, and half of 7 is 3.5. Double that is 7. Double 2 is 4. Double 3 is 6. I really did just double everything. So that's when in trouble, double. And sometimes it can help you through one you're just having trouble seeing and it's not making sense and you can't get to work. So double something. If that doesn't work, try tripling it. Now, the last little trick we're going to talk about here is one that's going to pop up a couple times in the homework. Now, this one is not as big of a deal, but it really does help balance this one too. If you're having trouble balancing a reaction containing water on the product side, and you see on the other side OH, then it really can make it easier. Sorry about that bell. It can really make it easier to balance if you write water as HOH. So in this particular problem, I'm going to cross out water and I'm going to think of it as HOH. Now, why did that make it easier? Because it's still water. Well, it allows us to see OH and balance OH and chunk OH with a hydroxide or OH that's on the other side. So remember, we're getting rid of this and we're writing it like that. And what that allows us to do is to see fundamentally, okay, I have, keep it simple. So we're going to start with something easy like zinc. 1 ZN here, 3 ZNs here. So I'm going to need a 3 there. Now with that 3, that means I have how many OHs? Well, I had 2 and I tripled it. So that means I've got 6 OHs. Well, what would I put in front of water written this way to give me 6 OHs? I put a 6 there. And that gives me 6 hydrogens. Because remember, I've taken care of those OHs. I don't need to worry about them anymore. But I didn't take care of those H's. Well, I got a 6 there. So what would I put here to get 6 H's? And then double check my PO4s and see if it works. So this is a really tricky one for students to balance. But written as HOH, it was fairly simple to see. Once I put a 3 in front of zinc hydroxide, that gave me 6 OHs. That should give me 6 waters over there because I need 6 OHs. So this is one of those devilishly difficult to balance things that if you look at it as HOH and chunk your OH, much, much, much easier to balance. This only works if you got OH on the other side and water opposite it. Now the last one, this is something you should do every single time. Double check to make sure all the atoms and ions are balanced. So it doesn't take long to do a quick double check. Did it really work? And if it did, you're all good. And then second, and this is an important one, the balanced chemical equation, by definition, is the lowest ratio of coefficients. So you might have accidentally doubled something and got it to balance, but if you notice, you could divide everything by 2 and it would still balance. You need to divide it by 2. So you have to have the lowest possible coefficient ratios. So case in point, if I had a 4, a 2, and a 4 here in balancing this, this would work. 8 hydrogens, 8 hydrogens, 4 oxygens, 4 oxygens, it is balanced. But a 4-2-4 can be reduced by dividing by 2 to a 2-1-2. And this will be correct. And this will be marked wrong on your paper. So always double check to make sure you can't reduce your coefficients because it still might balance, but you might have the wrong answer. So that is what I want you to do to follow some tricks to balancing equations. And next we'll get into reaction types in our next set of notes.